class will be based on that presentation, that slide. So this is probably our second review, right? So this is our review class 2. So in the presentation, just for what is that? That is actually chapter 1 from the book SCLAR. Actually, this is the presentation slides there. There actually we talked about different kind of, actually these are the very basic stuff that probably it's actually recalling of your previous courses. Most of the stuffs are from signal and system. There actually you covered these topics, deterministic or random signal, right? We already actually discussed about this part. What is a deterministic signal? Anytime a signal has a fixed value, for example this equation, at any moment for t I can actually find what is the value of xt. This is deterministic. But the signal we talked about all about previous classes, random signal cannot have a deterministic value. If not, then how to quantify a random signal? Two way. Statistically, we actually do that one by finding the mean value or the variance of that signal. Okay. So actually, there are like periodic signal and impulse input signal, energy signal, power spectral density, energy spectral density, all the stuff. Most of the stuff actually you already seen, already know from your signals and system. We will just review it just for recalling, probably refreshing your memory, right? So we will start from very beginning. Okay, beginning of a Ohm circuit. Okay, very simple circuit. I and V. So we have a current I, we have a resistor. Our Vt is the voltage across this circuit. This is It. Okay. From Ohm's law, what do you know? Ohm's law, we know that V equal to IR, right? V equal to IR. R is the resistance in our circuit. So, what is the instantaneous power in this circuit? Because this is I change in current, current change in time, and the voltage change in time means it's actually supposed to be an AC circuit. So instantaneous. What is the instantaneous power? Because in DC we actually directly derive the power, but for AC the power as the current or voltage that fluctuate, that's why we need an instantaneous power, right? What is instantaneous power? Equal to I square R, right? Or it can be I equal to VR, V square T by I equal to V by R, right? So V square by R square. So R cross. So it can be V by R. Now we find two equations, right? So P equal to IR or P equal to V by R. Both way. So instantaneous power can be I square R, or instantaneous power can be V by R. Now we will assume that R equal to 1. Its resistor value is the unit value. What will happen? The instantaneous power for T, it will be V square, I square. For this one, instantaneous power, P2 will be, actually it was V square, V square, it will be V square. So instantaneous power is the square of the current, instantaneous power is square of the voltage. When we assume R equal to 1, we are actually normalizing the circuit. Now irrespective. So the signal we are applying for our communication signal we are transmitting, it can be a current signal, it can be a voltage signal. Means actually the voltage by fluctuating voltage we can transmit the signal, by fluctuating the current we can also transmit the signal. So irrespective it's respective to a signal, whether it's a voltage or current signal, as signal as voltage or current signal, what we have, our instantaneous power is directly, just give it a name, x square t, right? This is same. This is actually, this expression is actually expressed it here or it express it here, doesn't matter, because our here the V and I, this instantaneous power is irrespective. So the signal we are transmitting is actually x squared t. Okay. Now, so we know it from the instantaneous power. So in physics, we know that power is capital P, power equal to work done in total time, like work done in total time t. Total time t. We know it, right? So what is work? So work is PT, right? PT. For signal, this will be our energy E. Like for signal, our energy E equal to PT. PT. For signal, total energy will be total power by in total time duration. Okay. So how to find total energy? If you want to find total energy, we know it, right? From the P is actually rate of change, rate of work, actually rate of work done. That's why divided by PT, right? So total total energy, for example, E. So E will be what? Total energy E equal to total power time, right? So we do not know total power, but we know the instantaneous power at that moment, at a particular moment, right? Instantaneous. We know the, so small p. So we know energy will be like total power, where because it's AC, so it's a instantaneous power with total time. We have to find the total time. How to we make the total time? We make it total duration, dt. If we integrate with total time duration, it will be, for example, we talked about a in our digital communication, we always use rectangular, right? Pulse. So in general, it's actually minus t by 2 to t by 2. So it could be minus t by 2 to t by 2. That will be our total energy. We can actually express the same equation in different way, like limit where t tends to infinity minus t by 2 x square dt. How we got this x square? How we got this x square? From here, pt, because we know it from pt. This is the expression, right? This is the expression. So if I find the total energy, what should be the total power or average power? Let's write average power. Average power. What is the average power? We know from equation P equal to W by T, means energy by T. So we will actually this equation, this energy equation, if we divide by T, then it will be our average. So 1 by T minus T by 2 by T by 2. This one, I am writing this equation, instantaneous power PT dt. Or we can write it limit t tends to infinity 1 by t minus t by 2 x square. I'm writing this equation, t dt. So we find energy equation. We find power, for example, P. Okay, energy and power equation. So this is actually very fundamental. Probably most of you actually know it from your signals and system. Most likely, this is the first thing you supposed to study in your signals and system, right? Guys, is my writing clear?
Yes, sir.
Yes, sir.
Okay. Now let's go a little bit deeper. Let's find. Probably this is also you studied in your signals and system. What is an energy signal? So just like this is actually a recapping of which semester you studied signals and system. 2 probably, or 2-1. Guys,
3-2.
3-2.
Sir. Yes, sir.
Just last semester, really?
Yes, sir. Yes, sir.
Okay, then I should not go on with this on this topic. Guys, at 1 minute, I have a call.
Sir, it's better if you give a recap, sir.
Okay, guys. So should I continue with this stuff?
Yes, sir, it's
Yes,
better.
sir.
Okay. So what is an energy signal? Someone give me the definition. A signal is said to be energy signal if total energy is what? Fill in the gaps.
Finite.
Finite. Energy cannot be infinite. We know from the law of energy conservation, right? Energy cannot be infinite, sorry. So E. So our E is that thing I know that has to be finite. Okay. So if E has to be finite, how do I write it in equation? If E is the equation, our energy that has to be greater than 0 has to be within infinity, right? So what is the average value of a finite dilution signal, guys? Average value of a finite, because signal can infinite dilution signal we cannot calculate, so somehow you have to limit it, right? So finite dilution signal. So someone said 0. You guys agree that average value of a finite signal is 0? You guys agree? Definitely.
Yes,
It
sir.
had to be, so this is actually exclusive. If energy is finite, the average value is 0. We will actually see. We will see in example also. We'll see in this. This is a statement, right? It actually, because we are matured enough, this statement is true because it nowadays it becomes common sense. Average value of a finite dilution signal has to be 0. Common sense. But let's see if the common sense actually comply with us, right? So let's draw a basic signal. We always actually talk about rectangular or square. Let's have it. This is a signal xt. So this is t minus infinity to plus infinity. Now imagine this signal is 1 duration with a height 2. I'm just taking any signal. Okay. So what is the total energy in this? We understand this, right? If this is an energy signal, there's the area of this stuff is called total energy. But how to find calculate? So total energy, for example, E. E will be what? For example, minus infinity to 0. What will happen? Minus infinity to 0. What will be the total energy? 0. Right? Nothing here. There is nothing here. Right? Plus from 0 to 1. So 0 to 1. What will be the height? 2 to x square dt plus 1 to infinity. 1 to infinity is again 0 dt. Actually, I didn't have to write it splittedly, just for understanding. So this amount will be 0. This will amount 0. 2 square. 2 square is 4. What will happen? And then this is 1. So power means 4 to the power 1 minus 4 to the power 0 equal to 4. So there will be 4 joule. Is it a finite or infinite quantity? It's a finite. This actually checks out. Means the statement we make checks out. Energy is finite. Okay. If energy is finite, what had to be different? What should be the power? What should be the power if energy is finite? Okay, let's see. We know from common sense, but we can also check it out, right? So, for example, average power. Average power. So, what is the average power? Means the total power. Total power by total time. Total time. Right? Okay. So, what is the total power in our cases here? Minus infinity to plus infinity. Instantaneous power in all time, all the time. Right? By integrating, we are actually taking all the time. So, to make it total power. What is the total time here? You see this signal? See signal?
Sir, 1 second.
Minus infinity to plus infinity. So if a signal is from minus infinity to plus infinity, what is actually the total time? T infinity, right? So if I have this quantity, like I have this value minus infinity to plus infinity, instantaneous power, we actually make it integral so that total power is considered divided by infinity. T is infinity, for example. What will be the value? 0. You see our common sense that we make this statement, that checks out. So what will be this 0? This will be that 0. So this stuff actually quite known to you. I'm just going through. So if a signal is a finite energy signal, its power has to be 0. Right? So this is actually all about what about our energy signal, right? So what about the power? What about the power? So a signal is said to be a power signal if power is finite. We're defining something, right, guys? So if we want to define something, that has to be finite quantity. We cannot define a infinite quantity, right? So if P is that power, so it has to be within 0 to infinity. Now, because we already defined it, E, we know E equal to what? P into T, right? This one, guys. E equal to PT. We just have seen it. This one. This one equal to PT, total energy. How is related with the time? Now you see here P is finite, right? And this T is actually infinity. What will be our quantity? E will be infinity, right? isn't it? Makes sense, right? So we want to, okay, let's give an example, then it will be nice. So what we are meant to, right? You see this here, we want to find a energy of something, right? Let's see, when we try to find power of something, what we mean actually. So for our case, we could, guys, we could actually have write, I could have write a signal like this, like this. Okay, like, because this is a periodic signal, periodic, but instead of writing this one, I prefer to write this one. You know why? Because we are transmitting digital bits. That's why. Otherwise, they are same. Like, we are only talking about this guy. Okay. So this is also a periodic signal. Now, same thing. XT is the signal which have a. The area is this one, having a like height A. Now we want to try to bound this signal, because if it's definitely is from minus infinity to plus infinity, but I cannot talk about something which is not bounded. So let's make it little bit bounded. So minus t by 2 to t by 2. That's how the signal is bounded. I'm just bounded it at this duration, t duration. I'm bounding it, t. Okay, so let's calculate the power here. P is capital P. P equal to will be what? We know from the previous equation, 1 by t, which is actually the energy equation, minus t by 2, because now it's bounded. It was supposed to be like infinity, but I'm not writing infinity because I just make it bounded. Otherwise, I cannot calculate it. So x square t dt is our, yeah, it's recording. So how to have it? 1 by t. Let's see how I divided it by. So from minus t by 2 by 2, for example, this is 0. So minus t by 2 to 0 is 0. Nothing there. There is nothing here. There is nothing, and this in this region, nothing here. So plus 0 to, like, 0 to t by 2. 0 to t by 2. What is 0 by 2 by 2? We know the height. So it's actually a square. Sometimes, guys, I will skip integration or differentiation, because it's very common things to know for you, because integration and differentiation. Okay, so it's a square, because this guy is 0. I don't have to consider it. So it's a square. I mean, I am taking it out. Okay, a square by t by 2. So a square by t into t by 2 tt cross. So a square by 2. Now, this a square by 2, is it a finite or infinite? Guys?
Finite.
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 So, yeah. So what we did actually, we actually checks this. Checks it, okay? So P is finite now. P is finite. So, imagine this quantity, if you take it here, finite, multiplied by 2 is T, which is infinite. So we will end up A. So for our cases, E will be infinite. Sorry. Oh, okay. So E will be infinite. So we know P equal to should be finite, and it should be infinite for a power signal. Okay. Now let's go, guys. Everyone have your book with you? Sklar. I don't know. You have the same edition of mine. Page 51. Page 51. Sklar. So here, example, exercise 1.1. What is saying? It's saying, guys, open. I have gave you the PDF. Please open your PDF. Do I also have a PDF? Yeah, I also have a PDF. Let me check. I also have a PDF. It's clear. It's clear. 51 chapter. Okay. Guys, see 1.1. So classify the following signals. Whether so you have to find the value, and you have to classify whether this signal this is a energy or power signal. They are not saying, so you have to find it whether these signals are energy signal or power signal. Okay. Guys, can you see that this stuff? Okay,
Yes,
so
sir.
for our first case, xt equal to a cos 2 pi ft having this value. Okay, let's see. So exercise 1, what is say xt? I have a book, actually hard copy. I can see it from there. Xt equal to a cos 2 pi f0 t. Here for is given that t equal to minus infinity to plus infinity. So it's minus infinity to plus infinity. Actually, now you have to clarify whether this is a energy signal or power signal. We do not have to derive actually. From the question, I can see whether it's a power signal or energy signal. What is that, guys? Power signal or energy signal? E or P?
Power signal.
Why you said that? Okay.
Because of
Other guys are confused? Yeah, Ethe Shamul. You can.
because it's spanning from minus infinity
Yeah.
to infinity.
By seeing this, of course, we can prove it from equation formula, but still I can see it. It cannot be energy signal. Energy cannot be unlimited. Anyway, we know it that okay, this is a power signal. Okay, let's see. Imagine, okay, we just first assumption is a power signal. So P of x. Let's see. What is the power signal equation? 1 by T. For our case, we know minus T by 2 x square. So x square will be a square cos square 2 pi f0 t dt, right? Okay, so a square by 2 should be outside, minus t by 2 plus t by 2. You see this this one, cos square, okay, t dt. Okay, so we will actually introduce 2 cos square theta. We will introduce 2 here. If I introduce 2 here, 2 cos square theta, I have to write 2 here, right? So I write 2. So 2 cos square theta will be 1 plus cos twice theta, means actually 4 pi f0 t dt. Okay, guys. Now I easily know it from there will be 2 term. I will be integrating this term first plus this term. From this term cos 4 pi, I know cos pi equal to 0. So whatever the term cos 4 pi, this integration, sorry, what I'm saying is integration of cos actually sine. So sine pi is 0. So this term, whatever the pi term 4 or whatever, this term is automatically comes to 0 with our integration. So I will not going to do that. Right. So a square by twice t. So this will be our this one. So t by 2 minus t by 2 will be 2 by twice t. So this will be our square by 2. Is it finite? So this is actually our power signal. Okay. Let's. It's easy, right? From any signal, I can say. So this signal was a power signal. What is happening? So this is a power signal. Okay. So see, let's see the next one. So exercise 1.2. It's saying that xt given xt equal to a cos 2 pi f0 t for minus t0 t0 by 2 for otherwise is 0, otherwise otherwise 0. Okay, so whether it's a energy signal or power signal, our previous one we decided find that our signal was a power signal because we use a power signal, we find it a finite value, that's why it's become power. So again, question whether it's a power signal or energy signal.
Energy signal.
Energy signal, definitely, because how we know it? We know it from its duration. Okay, it's actually it's also very easy, so probably you can find it. Ex, I'm just writing the formula. Our formula was minus infinity to plus infinity because I already know the limit, so I will not write it. So minus t0 by 2 plus t0 by 2 x square dt, right? X square dt, which is actually I'm writing the a square, right? So a square cos square 2 pi a0 t. So guys, you see this formation is now again similar to our previous one. So solve it, you will find this value square t by 2. Again, we find it, our energy signal is finite. Guys, so we can decide it. We can conclude that okay, this is a energy signal. So this is actually we decide this is energy signal, not this one. Got it? Probably this kind of problem you already solve it in your signals and system. It's not a it's very silly stuff. Okay, so next stuff we will actually review is also known to you, unit impulse. Actually, this kind of signal, energy signal, power signal, and impulse, these are actually very useful to our signal. I mean, in digital combination. That's why I'm just saying it. So I'm just I will try to draw a signal. Actually, we like it a lot about the pulse, because most of our cases digital signals are pulse signal. Say xt is a pulse. This is a pulse signal. Okay, as usual, minus t by 2 to t by 2. So this is the duration. So this will be the duration t, and I just took 1 by t is its height. I'm just taking it. Okay. So what is the area here? What is the area? Area we know, height into width. So it's a t into its height, 1 by t, 1 by t. So it's 1. If it's 1, then we can say it's a unit area signal. A signal which has a unit area. Now, I like to reduce its area by half, like the width actually. So this will be t by 4. It's a t by 2. So let's say this one is I. Before it was t by 2. So minus t by 4 to minus 4. Okay, minus t by 4. This one is actually t by 4. So this width here, this one width will be t by 2. It's no more t. If this happens, then okay, I don't know how much is the area. So the new area, I want to keep it the same area, 1. I want to keep it 1. So I know the width is t by 2. So width is t by 2. What should be the height? It should be 2 by t, isn't it? To make it as 1, isn't it? So height should be 2 by t. You see, before it was 1 by t. Height should be now 2 by 2. Means actually I had to double the height. Height was before here. So now height has to be here. Height has to be here. Height has to be. So now height has to be somewhere here. So before it was 1 by t, for example, 1 by t. Now it becomes 2 by t. You see what the trend is happening. This is duration, right? So if I make the duration, which is actually in our case, first it was t, then it was t by 2, means I am making the duration smaller, 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 right? Means if my duration tends to be 0, like goes to the 0, then the height will be what? If the duration goes to 0, then height will be, guys?
Will tend to infinity.
Infinity, definitely, to make it still the same unit area. Okay, this kind of signal is called unit impulse. Actually, probably you already know it, right? So I'm just trying to express it. For example, I'm saying, okay, limit t tends to duration. Duration is t, our case, for our case. So t tends to 0. Then this signal xt have what? Xt has a infinite amplitude. Infinite height means actually our amplitude also same thing. Height and amplitude is same. Amplitude is same. Okay. At what? At t equal to 0, right? It happens only here, right? It happens only here, right? At this point, at t equal to 0. Otherwise, it's 0. At t not equal to 0 means actually. So what I'm trying to say actually this. Try to say this. Our signal actually this signal becomes like this, which is infinite. At t equal to 0, if it's t that at 0 it has the amplitude high, like infinite amplitude. In other places is 0. That's actually is trying to say. Now this one actually we noted by delta function, del, right? So what is the area? So again, for our cases, minus infinity to like plus infinity. This xt signal tt has a unit area 1, which actually we just write it. So we just write it that this guy is actually this one del. So minus infinity to plus infinity is actually del function dt, or we can write it minus infinity to plus infinity, where the limit t tends to 0. This is actually same guy dt. What actually summarize from these properties that del of t has a 1, and this one is 2. Okay, we can write actually it here. Instead of writing it here, I can write it here. What if I draw it? If I draw it, I just draw it here. What it have? It has a delta function. So this function is actually our delta t, which have an infinite duration and infinite amplitude with area A, area unity, area 1. That's actually saying. Now I will give you 1 or 2 property. The unit impulse function has many properties. For you guys, for using in digital communication, not all the properties you guys will be needing. You will be need these properties, multiplication properties. You need multiplication properties. Probably you see in our you will also see in our, or probably I have gave you one previous example where I try to multiply xt with a delta f minus fc equation. So there will be a multiplication. That's why actually we are trying to find how the multiplicative formula works for. Okay, for example, xt is multiplied with a delta. Guys, this one you also know that this guy is also known as direct delta function, right? Delta. Is it famous known to you guys, direct delta function? So who invented this stuff? From the name, also it said it looks at del, that's why it's delta. So probably this guy, not probably, this is a famous guy, direct. I don't know, probably German guy. So tau 1. So multiply xt into del t minus t1. What should be the result? We know. Okay, let's write the result. I know from the formula, like memorizing formula, t minus 1 del t minus tau. We know it from formula. Okay, we know it from formula, multiplicative formula. Actually, how it looks like, how we interpret it, right? So how do we interpret it? Now let's say xt. Now xt is a periodic signal, continuous signal, xt. For our better understanding of simplicity, now this time I write it as a periodic signal, xt. This is our xt signal, and this, so this is our this signal, and this will be our this signal. So del t minus tau 1, t minus tau 1 at t1, at t1 it have a unit area, okay, which is actually, this is minus infinity to plus infinity signal. So we are actually trying to multiply this signal with this signal, this signal with this signal, multiply. What will happen? You see, from minus infinity to t1, what is the value here? Guys, minus infinity to t1, what is the value? Up to t1, from minus infinity to up to t1, what is the value? This area here, what is the value?
Sir, 0.
0. So you are multiplying 0 with a probably it has some value. So what will be the value?
0.
0, right? Okay, now deleting this one. So okay, let us this is our multiplication, from minus infinity to plus infinity, from minus infinity to t1, the multiplication is 0 here. Not writing anything. Okay, what happens at t1? At t1 is unit area, right? This one, this is for this delta at t1. Okay, let's find at t1 this signal has a, for example, amplitude a. So a into this one. So now we can multiply this guy into 1. So you see, for this signal at x t1, we can write x t1, its amplitude is a, isn't it, at this moment? So we are multiplying this at t1 and at t1 at delta, at t1 of this our xt, and at t1 of what will be our amplitude? A into, so this will be our signal, right? This will be our A. This will be our A1 and this del. What is this amplitude? 1. But the function is del actually. So del T minus, sorry, not minus, right? This is multiplication.
Yes, sir.
Then, and the next time from T1 to infinity is again 0. So multiplication is 0. I mean, our this area we got it 0. Up to this area we got it 0. But at this point we have our this function has a amplitude 1 and area A. So area A. So this will be its amplitude, and this is the function. So we can replace A1 with this one. So we know A, not A1, A, for example. A is actually xt1. So xt1 and del function, del t minus t1. Okay, so this is our multiplication, which actually checks out our formula. Got it? Well-known stuff. Okay, another properties is called shifting properties of delta function. Shifting, or it also called sampling properties. Sampling properties. What is the formula? The formula looks like this: minus infinity to plus infinity. If I signal xt, I multiply it with del t minus tau t1. The formula will be x t1. Okay, so this is actually also in your Sklar book. Okay, guys, is it also familiar to you? Shifting or sampling properties?
Yes, sir.
No?
Yes, sir.
Yes, sir.
Okay, just because I already know multiplication, imagine this is a multiplication. Just how to have the solution. Okay, minus infinity to plus infinity, because this is end of my tab, I cannot write sometimes. So you see, this one can be written as this one, right? X t1 del t minus tau 1, right? Here you see this one xt1 actually was constant value. So this is a constant value, right? So I missed something. Oh, dt is missing. Dt is missing. So if this is constant, then what happens? The make it outside, eh? Keep it outside. So x t1, then minus infinity to plus infinity del t minus tau 1 dt. So what is the value? What is it doing? All the area of this del. What is the value? You know, it's the impulse, unit impulse. So its value is 1. The area under, isn't it? Isn't it? We studied so far. This guy. All its area is 1. That's 1. So x t1. You see, this formula checks out. It's also known to you, right? Okay. In your book, there is an example. Let's see. What is our PDF? Our PDF. Yeah, this one. So there is an example given. Eh? So let's just see one or two example. So see some example. Eh? What is the first example? The first example is actually 1 point. So exercise. Exercise 1.13. 1.13. So exercise 1A. So A is saying minus infinity to plus infinity cos 60 del t minus 3. Very, very easy actually. So what is actually which formula we are trying to use it? The last one, this one, this one, we will use this one. So integration of something into del, which will be this function, the xt will be replaced by t1, right? So we can say it will be this is, for example, xt. The answer is xt, right? Xt is actually cos 6. We are not writing t, because you see this was what? T1, right? T1 was this one. T1 was, so here 3 is the T1. So 3, instead of T, we're writing 3. So it's actually cos 18. Whatever the value of cos 18. Find it. Easy, right, guys? So there is a, B, C, they are actually same nature. D little bit different with exponential. So minus infinity to plus infinity, exponential minus t square del t minus 2 dt. Same thing, but still though it looks a little bit different. So exponential means e to the power minus t, but t is actually replaced by 2. So 2 square. So e to the power minus 4. You see the last formula. I am just, so I don't know what is the e to the minus 4. Find it. Calculate it. Guys, it's easy. Solving unit response, impulse response, actually quite easy. Okay, let's do, because we already have seen energy signal and power signal. So we like to know this one now. Energy spectral density. Energy spectral density. So we will consider an energy signal. So consider an energy signal xt. So this is our xt signal. If we do a Fourier transform of our energy signal, or whatever signal, not energy signal, any signal xt, what will be the Fourier transform? It will be x of f, right? Now, how we actually find x of f something like Fourier transform? How can I find a Fourier of something? It's a common formula, right? You know it from the DSP. The most common formula, if I want to have some Fourier transform of some signal xt, what will I do? Minus infinity to plus infinity, amplitude xt, and e to the power minus j 2 pi ft dt. If I want to find a Fourier transform, if I do the inverse Fourier, remember we talked about a lot about this guy, right? Is it very known to you guys? Yes, this is our Fourier transform. If I do opposite one, that will be our inverse Fourier. From this guy to the previous, go back. So we just, if I have a time domain signal, how can I convert it to the frequency domain signal? How can I convert it to a frequency domain signal? That's easy. Now, what is this xt? This xt. From the very basic of our signal, we say it can be a voltage signal, it can be a current signal, I don't know. Because of our normalization of resistance, it was equal for us. So you see, if it's a voltage signal, if xt is a time signal, what this xf give us actually? time signal, it gives actually, if it's for example, imagine it's a voltage signal. So f what it give actually? Voltage signal with time, right? So it's actually voltage time signal. It's a voltage signal, right? Xt, and you integrate the whole xt in time. So it's actually voltage time signal. The frequency domain signal is a voltage time signal. If it's a current signal, then whole the frequency domain signal will be a like ampere time signal. The unit will be ampere time. For the frequency domain, it will be voltage time. We can actually rewrite it. Voltage time, instead of voltage time, we can write it voltage hertz per hertz. So it's a current, it's an ampere per hertz signal. You see our voltage signal, how we express it in frequency domain, like from time domain to frequency domain, how their unit changes. If it express our voltage signal is voltage in time, it will be frequency domain is voltage per hertz. That's how the conversion is happening, isn't it? It's understandable, right, guys? So now we will probably Percival theorem, right? Percival theorem.
Yes, sir.
Percival's theorem. What is the Percival theorem say? In general, for a signal, we can directly write it, but what it say? Percival theorem. Percival theorem actually in easy English, it's actually this: sum or integral of square of a function is equal to the sum or integral of the square of its transform. This is actually generalized statement for a sum or integral of a square of a function is equal to the sum or integral of the square of its transformation. Okay, let me write it. What it mean actually? Sum or integral of a square wave, which is actually for our cases time domain signal, is sum or integral of its transform. For our cases, this transform is Fourier transform, df. That's actually it's trying to say. Understand it? How what it mean actually, guys? So okay, so here what I write actually. What is this amount? This is actually our energy signal, E. Energy of this signal is actually, so now this amount gives us nothing but the energy per, what is the unit here? T, right? dt. So per unit time. Energy per unit time is actually this amount gives. So energy per unit time, you integrate with the whole time with whatever the limit. You have to, for if it's like energy, you have to quantify that limit. Then you will actually get the, you will get what? You will actually get the energy spectral density. You see here what this guy trying to say us. It's actually energy per unit what? Frequency, right? It's actually having in frequency. Okay, in communication, instead of frequency, we actually express it by bandwidth. Same term. So bandwidth will be in hertz. You see this one? In hertz. That's actually we find. It's actually frequency domain signal. This one, which actually this one. Right? For energy spectral density, we actually express it by psi of f in our frequency domain. So I can write it. I can write this energy spectral density E of x, actually nothing but minus infinity to plus infinity psi of f df. This one actually I'm rewriting it. Understand, all right, guys? So let's see what about the power spectral density. Power spectral density. So here we actually again consider a signal xt. This time, because we are talking about power, we had to little bit careful. So we say this is a bounded infinite duration signal. Now, because this is a infinite duration signal, what we cannot do? We cannot find total energy because it's a power signal. So to find the total energy, what we have to do if we want to find it? To find, for example, energy spectral density of this signal, the signal we just defined. If we want to find the, we know that power spectral density or power of power signal is easy to derive from the energy signal, right? We just make it rate of change of time. So that's why we are actually looking for energy spectral density. To find an energy spectral density, what we have to do? Consider a truncated version. Truncated version. What I mean actually, truncated version means actually, for example, this was a signal. Let me draw it in time. This one, sinusoid type. It will be a little bit easier for me to explain. So this is a it has a minus infinity to plus infinity. I cannot find a energy spectral density or energy from this one. What we will do? I will do truncated. I will take a piece of it. Okay, just slicing it, slice, and I take a piece of it. So that piece of xt signal, we called it as x of t, x subscript t. So how do I truncate it? I will truncate it from here. I will truncate it like small space minus t by 2 up to t by 2. Oh no, this is, yeah, t by 2. So we actually, what we are doing actually, we are taking a slice of this signal. This was our xt, which was actually infinite signal. I cannot calculate an infinite signal. What I'll do, I chop it. I just took a small part. Then we can analyze it. From that part, it is easy to find an energy signal. From the energy signal, it's easy to find the power signal. Means if I find the energy spectral density, I can find the power spectral density. So what this signal will have? So xt will be actually the xt version. Same signal within this duration. Minus t by 2, 0, t by 2. Isn't it? Otherwise, it's 0. We are not taking any other part otherwise. So this our xt version is a truncated version of xt, means sliced version. So how can I find a sliced version of our signal? So in mathematically, what we do, our xt signal, will be our original signal multiplied by a rectangular function. Rectangular. I have shown you this function before. This one. Imagine. So what I did actually, I actually took another signal. I took actually this signal. So I took actually this our function. For example, GT. GT has a actually an a rectangle t by total t. This t is actually this t. This t. So this t. So this is the expression. Here a we imagine is unit area. So this a will be 1. Just for sake of simplicity. Nothing else. If I multiply my this signal, which is actually infinite signal, with a function gt, I will have a truncated version, a small like a slice of that version. Okay. So if I have this is time domain signal. So if I do Fourier transform, what will I have? X of t f, this signal, right? If I make it a Fourier. So what I have, energy of x of t, that truncated signal, minus infinity to plus infinity, x of t square dt. Right? I write it the previous equation from the previous slide. This one. So I know this is actually the same as of its Fourier. So let's solve it. Just because we just truncated it, so it's not anymore infinity. So it's actually minus t by 2 by t by 2 excess, which is actually of this version, xt actually this version of this limit, right? dt plus infinity to plus infinity xtf square df. So what I do, I will actually add, in this equation, I will add a limit in both sides. I will add a limit t tends to infinity. Okay, I will add this one to make it a power portion. So minus t by 2, minus t by, sorry, plus t by 2. It's not minus t by 2. I'm actually writing the same equation, this one. dt will be limit t tends to infinity 1 by t minus infinity to plus infinity x of t f square df. You see here, the whole, this part, what is this part saying? This is a power signal, right? Now, if I write the whole power signal, what I actually am writing here, this one, like this one will be limit t tends to infinity x of t in frequency domain square df. This t actually I'm writing here. This one, oh, I forget, minus infinity to plus infinity. This part is the power per unit bandwidth, because it's on if we have a power per unit bandwidth, if we multiply it with the whole f, then you will get the whole power of this signal. So this gives our power spectral density. Like we can express it as a g of x f, this part, inside part. So I'm writing the inside part, limit t tends to infinity xt f square by t. So this is our power spectral density. So I can write this px also. Px equal to minus infinity to plus infinity g of x f df. So I have the power spectral density.
Sir,
Yeah,
sorry to interrupt, sir. We have another class right now, sir.
you have another class, okay? Okay, so we will finish here then. We will finish here. Let's stop our recording.